The key element, EV battery testing. My name is Jack Porter. I'm an applications engineer at ATS. I've spent just about my entire career developing production test processes and equipment and systems for leading OEMs. Over the last decade or so, my concentration has been on the electrification of just about everything. Most notably, most recently, this has been with respect to electric vehicle powertrains, power generation, power conversion, and power storage. And over my many years of production testing, I've been through a few battles, got a few scars to prove it, and I've learned a few things. Two of my favorite things that I've learned is one, that Ohm's law really works, and second, that the only constant is change. And I know it's a real cliche, but it's especially true today with respect to production testing of batteries. So today I'm going to be talking about all this change that's going on and what does that mean with respect to the electric vehicle market and what does it mean in terms of what we need to do for production testing. So if we look around at the press releases, we look at trade journals, we go to different shows, we see exciting changes occurring everywhere and across a lot of different directions with respect to the electric vehicle market and batteries in particular. We see changes in the baseline chemistries. We see changes in the end application and usage, be it mobility applications or storage applications or range extension. We see changes in the packaging, how these products are put together, what their form and function is for their end use. The system connections in terms of what the interconnects are, what needs to happen to these in order to integrate them in terms of what their end application is. And ultimately, the charge and discharge requirements, because that's what the end game is here, is in terms of how we get electricity out in order to drive our application and how we recharge it. So with battery technology improving at this rapid pace, what effect does this have on us? Well, we've got a convergence of technology and timing. And so we see the technology is changing all over, and the timing is based on the demand that we're seeing today. So let's take a look. I mean, a typical battery assembly process might take 2 to 3 years from the project start, where we have a request for proposal, to the point where we get up to a full production ramp up. And this timeline is too long for the existing demand. And the changes that are going on would make that project a moving target if we actually took that long based on the evolutions that are occurring today. So what we need to take a look at is how to transform our existing manufacturing spaces that we have or that we're going to produce in order to reach full production in a shorter time frame, but not being able to rely and leverage on the mature technologies and processes that we had in the past, because these are not mature technologies and new processes are being developed to implement them. Due to this pace of high demand, we need to look how to adapt and how to deploy this within our organizations and what does it mean for production testing in order to ensure our success. So a shift in perspective, perhaps. We can take a look at what we already have and our organizations, our capacities, and what limitations we have there. We have people, we've got lots of good people that work for us, lots of knowledge, and the ability to scale up or down as required based on the products that we're looking to produce. And so we need to focus on the areas we have to learn and modify and adapt with that. If we look at how we interact with other companies with respect to suppliers or end users, what teams do we have in place? How does that work today? How can that handle something where things are changing quickly and the changes will have a ripple effect, both from between tooling suppliers, between manufacturers, and between end users? So we need to take a look at this and understand this as a background as we go to adapt the test processes we're going to deploy. So let's take a few minutes and take a look at those parameters and processes. These things are evolving. If we walk through some of the change areas, we can see that chemistries are changing, packaging is changing, monitoring, which in this case is for the most part intelligence that's on the part in terms of what we can do, what do we have to monitor as part of the end use on this product, what can we monitor in terms of producing this product. And we put this on top of our short time frames. This means many times we have to adapt the laboratory and design methodologies directly into the high volume production process. And this can present some real difficulties in separating product design validation parameters from production testing parameters. What are the parameters that count in order for us to ensure that we built the battery correctly, not necessarily that the battery was designed correctly? We take a look at some of the existing battery test parameters. We have some de facto standards with respect to the state of charge. This is a key one. You know, where's the battery at? How much current capability does it have within it? The state of health is a little bit more of a longer term thing that we look at to say how the battery is performing. Is there any degradation occurring? If there is, how much has occurred? What kind of lifetime can I expect out of the battery? What can I do in order to maximize that lifetime coming out? What is that? What is it that we test for in order to determine those things? Leak tests, we have a lot of thermal processing within these parts. Typically, when you have any kind of power moving around, there's some inefficiencies. Generate heat. We certainly have that within the battery packs, and we have a lot of systems that are in place for trying to manage that energy. And most notably is the leak tests. Where are those, and how many are required is kind of unique and kind of what we need to pay attention to. And then if we look at these changing conditions, we have to figure out how we're going to handle them while we're doing a design and trying to put together a system. For example, on the slide, we showed just some of the changes across the electric vehicles over a short period of time. We see some functionality comes and goes, the interconnects are changing, and this is what we're going to have as we go to walk through and design up our test systems. So we look at these products and we look at end of line testing, and the end of line testing says ship the product. It's good. It's ready to go to its intended use. And these products are rather large and bulky and rather expensive. And we cannot succeed if the only test we do is by doing a test at the end of the line. So we have to look at in-process test. In-process test is going to result in a greater first-time capability at the end of the line. It's going to identify issues or defects in the part sooner, earlier in the value stream. It's going to provide some feedback to be able to correct those defects in the build process, which ultimately allows us to minimize scrap and rework and maximize our uptime and OEE. The in-process test enhances the end-of-line test. To succeed, you need to have both. A key way to deal with the convergence of battery timing and technology is using the same test equipment across the line. Another good way to do this would be to have a single point of contact for all test functions, and dedicated engineers will understand the part through its build process, and ultimately leading to a deeper understanding of the part characteristics by all involved with this line. So what this really implies is that a single company is your best bet for supplying both your in-process and end-of-line test. And this is something that ATS is uniquely capable to do. We do both in-process tests and end-of-line tests. So it's really important that we do the in-process testing and the line test, but the challenge is to find the right locations and procedures for the test. And ATS is here to help you do that. Well, let's talk about it. How can we go about doing that? And so the place to start is to look at our part process, our processes, what the part is, how it's going to be built. And we have to be keenly aware to break any biases that we might bring forth from previous programs, especially if we're coming from a place that does not deal with some of the uniqueness of a battery product. So the first thing that always impresses me is the number of parts that are involved throughout the process. So when we start at the beginning, we have something that we're processing parts at a per second rate. So we start out with pouches or cells, and we need a tremendous number of them in order to make up a completed battery. So we start out with thousands of them in a end product. That means we need to be testing thousands of them up at the start. As we move down the assembly process, these products are highly modular. We tend to build up little packs or sections or modules that consist of some number of cells or pouches or energy storage devices. You know, maybe it's 300, maybe it's 500 per section or module. So now our rate that we need to process and run tests at starts to slow down a little bit. Now we're looking at the number of seconds per part that we're going to be dealing with. And then when we get to the end where we have a single completed pack, we're looking at maybe minutes per part. Not only do we have to look at the quantity of parts we're looking at, we've got some intermingled processes. Not all of these things are purely discrete processes. We start up at the battery formation end, and we have processes that go on that could take hours or days to complete, and they're not necessarily very active. They might be kind of passive once you control for environmental factors, or maybe there's just some monitoring that we're doing on the part. Then as we go down, we might have some cure time for some sealants or some thermal materials that we've added onto this part. And so we kind of get this very high, very quick going, and then we have these interleaved in there where we have long periods of time where the part is not actively being operated on per se by the line. Additionally, we're talking about acting on the part. As we go down, we've got part handling that changes, you know. So we start out at the beginning of the line with something that's very small and light, and at the end of the line, we have something that's very large and heavy. Part connections change also. If we look at the testing across these parts, we're kind of testing the same physical quantities as we go down the line, but we have different connections for doing this. We've got high voltage DC connections, typically more towards the end of the line as the voltages get built up. We've got low voltage DC connections that are used both for control and for charge and discharge. We have different fluids that we are placing into the battery that we're using for the thermal materials or adhesives. We have physical changes in terms of the form factor of these connections that we have to do. So we have to take a look at this with respect to our tests. If we look at the part connections at the beginning of the line, they tend to be very dense and very small areas that we need to connect to. And as we go down the line, the number of channels that we need to connect to starts to drop down, but the connection size itself starts to increase. So we got this continual flux that goes through as we're going through. And our key today is to figure out how to handle this with our test equipment and our test connections in order to make this easy and something that can handle the adapting changes that are going on. And not only do we have these physical changes going on, the part also is increasing the amount of power that it's storing. So this is a stored energy device. And as you go down the line, the amount of stored energy sitting in front of you is increasing. We look at all these connections. We have to look at, gee, do I do this manually? Do I do this automated? Can I physically do it manually? Perhaps we look at the beginning of the line where we have very small, very tight connections to be made. Perhaps we can't do that automated. I need some tooling that's going to do that for me. Historically, we would take low volume production or pilot builds and do that with manual connections just due to the capital expense. And then we go to automated when we ramp our production volumes up. With the rate and the demand that's going today, we need to be able to plan how I can flex this, how I can go from manual to automatic, or maybe straight to automatic, or manual tooling that's adapted and ready to plug into automation. So in order to answer these questions, we have to understand what the tests are. So let's look a little deeper at the actual test going on. So in the production of electric vehicle batteries, the battery testing is not just testing a battery. The battery is just one element. This is a complex system. We have a lot of assembly validation, and these are things that are sometimes people consider them tests, sometimes they are, sometimes they're more validation that the part was put together, and there's usually an overlap between these. And if we look at what we have today, there's a wide range of existing technologies that we can use for many of these functions, but perhaps applied to some different scenarios than what we're used to. Some notables would be welding. How do we make contact and define non-rigid structures earlier in the process that might be interconnected up and become stiff later on in the process? Additionally, we're going to have some technology crossovers, perhaps from other industries. So we look at the different things we're doing for validating the assembly. We might want to look to the electronics industry where they're used to high density part placement and interconnects. We may want to look to the chemical industries for what they do with respect to electrochemical impedance spectroscopy for determining what we're dealing with. We take a look at dispense of chemicals and how that occurs. So we look at this, we'll have a lot of things that will be on the line, and we have to determine what is required for measurement versus just validation. And as we do this, just like to point out that there may be some safety issues associated with this part being active that might preclude some perhaps simple solutions we might think we might be able to use. So looking at our testing deployed across the various different systems on the battery, this diagram has the assembly validation type systems kind of color coded in orange, and these may or may not have data associated with them. Usually there's limited data. Sometimes it's as simple as something is there or not there, or something achieved a specific measurement or did not. The things that are in green are things that tend to have a more detailed measurement capability, which I would define as having more complex analysis, greater accuracies, perhaps some intervariable data analysis, or some stimulus and measurement response. And as we look across the different tests we do on this, some interesting things occur. So we talked about the how the part is built up. It starts out small and gets large at the end. And this is kind of similar for the measurements as well. We said we have the comparable measurements physically in terms of the physics going across, voltages, currents, that kind of thing. And as we look at what we're doing in the production line, we see that the magnitudes of our measurements are going up as we start out. So we start out small at the beginning of the line with single digit voltages and currents. And by the time we get to the end of the line, we've increased by 3 orders of magnitude. And so is it possible we can get some test equipment that can handle this range? Depends on your accuracies that you need. And your accuracies that you need are based on your product and where its capabilities lie. Additionally, structural integrity. Now, we kind of looked at that a little bit on assembly validation, but in this case, the structure may not just be, and typically is not just for protecting the part. It's also part of the electrical system. We use for bonding and for isolation. So we probably need to test that as well. So we want to prove that we built it correctly, and we can do that in our assembly validation. But then we need to electrically verify with a test that that is indeed the case. Leak tests are key. There's almost always coolant or fluids associated with cooling these products. We charge and discharge large amounts of power, and as efficient as these are, most of the power that does not get converted properly is due to the inefficiencies turns into heat. So we look at the leak tests on this. We usually have coolant channels, and that may go to the modular portion of this where we have our different sections, and we probably want to test those when we get a section complete before we put it together in a pack to make sure within a given section we have no problems. Then as we interconnect up a bunch of sections, we're going to need to leak test to make sure that the interconnects between those sections are correct. And when we finally get to the pack itself, then we need to make sure that the connections from all of those sections to the outside world is correct and it does not leak. Additionally, in terms of leak tests, not only do we want to leak test the coolant channels, we also want to make sure that the pack, the enclosure itself leaks, does not leak. And this would be, to make sure that any gases that are contained within there are only outgassed as appropriate, or that the part cannot get is protected from any environmental considerations in terms of where it's going to be used in its end application. Key element on these parts. Now, these are smart parts, and we find that we have some intelligence on them with respect to battery management systems. And typically we find these down at the section level. So we have something down that's monitoring a section, some number of batteries in terms of their actual voltages, perhaps the resistances, some charge management structure for allocating the distribution across and maximizing life. And we want to test that at the section level. We want to make sure that's all working good at that point in time. Some key things to look at is, can I use that information that resident intelligence is as part of my test? Does it generate data I can use? You're going to get status information. You're going to get diagnostics information. We're going to want to incorporate that into our tests as part. Of course, we have to go through and prove that indeed our intelligence is not lying to us and it's giving us good data first. Once we've proven that, then we can use all that data as part of our test sequencing and part of our stating that the part is correct. As we go from the sections, we come up to the overall pack. And so usually there's a communications architecture between the sections up to a battery management system. And so similar kind of considerations we talked about for the sections, we want to do that up at the top end with the battery management system. The battery management system typically, though, will also have some interface for whatever the end application is. We need to test those as well. Some notables would be the safety interlocks that are associated with this. And so we look at all this, we have to understand and we have to try and figure out the impacts required to test this. And we look across the entire lane, and our best bet to impact is to look at using high accuracy equipment across the board. This will allow for changes due to the evolving nature to be able to flex up or down and still get us the data we need to say good part or bad part. Scalability is highly desirable, and we can do that certainly to a point, maybe not across the entire production line, but certainly within sections and certainly within battery packs. We're going to take the amount of power that we can put into a battery and the amount of power we can take out of a battery and scale that up or scale that down and still get usable, good data and prove that these parts are correct. And then lastly, a key that's kind of coming online more and more, especially with the intelligence on these parts, is configurability. What is it that we can do with respect to that? Sometimes that's going to be a product design issue as much as it is a test issue, which goes back to what we're talking about in terms of how's your team set up? How do you interact with the other avenues within your organization, within your supply base, within your end user, in order to be able to leverage that and come up with things that allow us to be able to do what we need in the factory and still protect for the part. So we need to come up with a different strategic initiative for testing our batteries. We need to remember our shifts in perspective, right? And take a look at what we have on the slide. On the left-hand side, we kind of show things that are going from a prototype stage to a manual small volume production stage to a high volume stage. And the issue we have today is these things could be happening on top of each other. We could be trying to design the final highly automated high volume line at the same time we're still proving things back in the lab. And so our proof of principles and that timeline is highly compressed and is often on top of each other. So we need to identify issues and problems quickly, early, and this is a solving early for failure. We need to be able to take our equipment and be able to flex it from our pilot line to our production volumes. Scalability is key for this. The difficulty we'll have in here is trying to make sure that we do not bring those design validation measurements into our production, and this can be hard early on. And maybe it's the kind of thing as we ramp up that we phase out what's required for that and get in what it is that's required for this. But in order to do that, perhaps we need some other tools at our disposal. Some other considerations to look at are kind of illustrated on the right side here, where we talked about the scalability and being able to take things up and down a little bit. Talk about some of the safety protocols, what's required to handle these parts properly, what to do if we have thermal events occurring, this kind of thing. And then what's the effect on our facilities? We're talking about a lot of power we're putting into these parts and taking out. Do I have the power grid within my existing facility to be able to handle that? Most of the time, we're able to take the discharges out of the batteries and consume it within our plant, which is great. Reuse that electricity. If not, if my discharges are large enough, am I going to overwhelm my facility and look to try and push that out into the local utility through the point of connection? You get an idea on that and plan for that. And this is especially important when we go from a small production to a large production quickly, to make sure some of those things can take a while to get in place and we can get that going quickly. You take a look at the intelligence that's inherent on these parts and taking advantage of that. And this is where some of the newer technologies that are coming out with respect to the industrial Internet of Things and the interconnection and the data that we can grab there and use, and to increase our capabilities to modify and change as things are changing. We take a look artificial intelligence or deep learning type algorithms and systems. And this is beyond just logistics and delivering product to the line. This is in terms of trying to resolve between those test parameters from the design validation phase versus the production phase, which ones are important. And not only that, now the feedback from the continuous learning process that was extended out there in time, we need to bring that back in sooner. And this is where some of these deep learning and artificial intelligence processes may be able to help us to introduce this quicker, to accelerate that and make it so that we can win. So ATS is uniquely suited to provide a solution throughout the entire life cycle of a product. We have a great team of people and a lot of skill and a lot of knowledge. We produce really good products and we like doing this stuff. We're good at it. We've been doing it for a long time. We have a great staff of people with respect to project management and installation and service in terms of getting this stuff executed and built and installed and maintained. We're located around the world, so wherever you are or wherever you want to do your product testing, we're there for you. And we're financially stable. We've been around a long time. We're not going anywhere. Couple our people and our company structure with our depth of experience in battery assembly, storage, and test systems, and it's a winning combination for everybody. Every day matters.